So today will be our last day of probability. So let's get into it. Last time, we talked about expected value. And today, we are going to talk about the other thing that we introduced yesterday, which is variance. So we will get into that in a second, although actually, we are going to start with a little bit more expected value. So you may remember from last time that we talked about the linearity of expectation, and I emphasized that we did not need random variables to be independent for that to be true. So now we're going to talk about multiplicativity of expectation, and for this we do need independence. So let's define that really fast. We've defined it before for events in a sample space, but now let's define it for random variables. So random variables x and y are independent if, so the definition is basically similar. We just have to adapt what we mean on each side to the case of random variables. So they are independent. Remember, the old formulation was E intersect F equals probability of E, probability of F. And the new formulation, the intersection just becomes an and then this side stays essentially similar. So what we get in this case is the probability of x equals some outcome R1 and y equals some outcome R2. This probability is equal to the probability that x is equal to R1 times the probability that y is equal to R2 for any R1 and R2 real numbers. So basically a similar definition. So let's give an example though, in any case. So roll 2 dice. X1 will be the random variable that is the first die. So it will be uniformly distributed on the outcomes 1, 2, 3, 4, 5, 6. And X2 will be the second die. So it will be the same distribution, but these will be independent random variables. So then let's say y equals x1 plus x2 is the sum of the 2 dice. Okay, then x1 and x2 are independent. Because for any a and b in the range 1 to 6, we have the probability that x1 equals a and x2 equals b is 1 out of 36, because there are 36 possible outcomes, and this is one of them. And that's equal to 1/6 times 1/6, which is the probability that x1 is a, saying that the first die roll takes a certain value, times the probability that x2 equals b, which is the probability that the second die roll takes a certain value. And so this equality means that they are independent by our definition up here. But x1 and y are not independent So remember, x1 is the first die, and y is the sum of both dice. And how can we see this? Well, we just need to choose two particular values where this product does not hold. So, for example, the probability that x1 equals 1, so the first die rolls a 1, and y equals 12, which is to say that the sum of the dice is 12. So the probability of this is 0. Because if the first die is a 1, then the second die can only go as high as 6, since let's say we're using two 6-sided dice. So you can't have the first die be a 1 and the sum be 12. There's no way to do that. On the other hand, the probability of rolling a 1 on the first die is 1/6, and the probability of getting a 12 on both dice is 1/36. So we're writing down probability of x1 equals 1, and the probability of y equals 36. So this thing is not 0, so the two sides are not equal, and these random variables are therefore not independent. So now that we have this definition, we can state our theorem, and let's put it in context of what we did before. So recall the linearity of expectation for any random variables x and y, not assumed to be independent. We have, so let me write that, not necessarily independent. We have the expected value of x plus y is equal to the sum of the expected values. And the theorem about multiplicativity is if x and y are independent, then we have a similar equation for multiplying x and y. So the expected value of x times y is equal to the expected value of x times the expected value of y. So this is another useful thing for computing with expectations and working with expectations, but I don't want to go into it too much. I want to continue on to talking about variance, but we will see this theorem showing up in a minute when we are talking about variance.